hope that I'm audible to all of you. And today we are going to start a topic that is actually very intuitive and very easy to understand, as well as very scoring. So this last unit may seems to be daunting at the face of it, but soon you are going to realize that the question that is going to be asked in examination are going to be quite simple. Okay, and the concept is easy enough to understand even for someone who is just starting out. Okay, so let me share my screen now, and let me open a notebook here. Okay, so I hope that this notebook should be visible to all of you. Is it? सबको दिख रहा है आपको? हेलो आर्या, बताइए वेदांत दिख रहा है नोटबुक आप लोग को? Do respond, otherwise it will be kind of difficult for me to continue with this lecture. Okay. Yes. Okay. So the idea here is that of the, so we are going to discuss this topic of error control coding. So I don't know what is the name of this unit is, but the topic that we are going to discuss is related error control coding. Okay, and I hope that this is very, very clear to all of you. So there are kind of, people do ask it with different name, like some of us know this error control coding by error correcting code. Coding or code, okay, codes, and we also know this by the name of channel code, because that is where it is utilized with respect to communication. But that's one part of this. Okay, actually it is utilized anywhere where you are going to need your data production. Okay, protection. So all the storage system, everything where you can think of this data. Okay, and protecting that data is important in that situation. Okay, then you will see that error control coding is kind of used that there. Okay, so initially it was invented by, what you can say, Shannon only. Okay, so Shannon in just one of his book was able to complete this whole communication conundrum. So it was kind of time of the World War II, and just at the end of it, he was able to publish that paper in 1947 or 49, I think. So in that book, he has kind of discussed each and every issue. So this is also called known as channel codes. Okay. So let me give you an block diagrammatic introduction of what a communication system is. Okay, so the simplest model is that you have a transmitter and you have a receiver, and in between that there is a channel. Okay, a slightly complex model is that you have a source. So this source is something of, which we already familiar with. So this, let's say we are communicating in English language. So this is going to be English alphabet, isn't it? If it is written, isn't it? So this is going to be our source, which is simply transmitting some message. If it is analog, it is generally converted to uh, discrete samples. And after, once we get sample, we have finite level of discrete values only. So these samples that comes from different symbol. For example, English alphabet, which is inherently digital, you have 26 symbol, isn't it? So we have source, and once we get source, this source is not in binary or anything like that. So the very first task that we want to do is that we want to perform source encoding so as to efficiently represent whatever message is there. Okay. So after source, we will apply a source coding step here. Okay. Source. So this is going to be source coding. I hope it is visible to all of you. Otherwise, I will draw a bit bigger. Okay. So once we have efficiently represented our data, let's say we have to kind of transmit this message, or maybe this is a song which we want to store in a in digital memory or somewhere, isn't it? Or maybe on a magnetic tape or something like that. Okay. So losses are inherent to these system, or noise is kind of inherent. If you are transmitting, then there is going to be channel noise, isn't it? You can't really remove that noise. There is no magic trick there. Okay. So there is going to be error. The only thing that we can do is that we can employ some algorithm or some techniques through which we will be able to understand, okay, there is an error here, or we may be able to even correct that, okay, to get our original message. Okay. So to do that, what we do is we apply something called as source coding. Okay, sorry, channel coding or error control coding, whatever you want to call this. So I will write this ECC, error control coding. And after that, we modulate this message, okay, on a carrier to transmit it. Okay. And if you are not, if you are simply storing it, then you are not going to modulate this, isn't it? So this is specifically related to communication. But if you are doing storage only, then you will not be doing modulation here. And after modulation, you are going to have this channel. Okay. So you have this channel here. After channel, there will be some noise. And then after that, we do this modulation, demodulation here. So whatever step we have performed there, we have to kind of perform an inverse step here as well. So this is going to be demodulation. And after that, we will we have error control coding we have applied. We will apply inverse of that. So this was channel coding, and now we will have decoding here. So we will have ECC, which is basically channel coding. With respect to communication, we generally call this channel coding only. In general, it is known as error control coding, and there are different way of achieving this. So here we are going to have channel decoding. Okay. And then we will have our source decoding. Okay. Sorry. We will have our source decoder or decoding. Let me write decoder only. And then in the end, we will have what we would like to call as sink. Okay. So here we have source and here we have sink. So this is going to be our transmitter and sink is going to be our receiver. Okay. So this is the channel where there is going to be noise. Okay. So I hope that all of us are kind of, I mean, at this point of time, noise is pretty much clear and we can't really avoid it. If there is no noise, there is no need of communication. Everything is going to be deterministic only, isn't it? So noise is what you can say necessary evil. That should be there. Otherwise, there is no going to be communication engineering or anything. There wouldn't have been any progress in communication and all that. Okay, so noise is the necessary evil that is driving all these development in these related fields. Okay, now so we have source and we are doing source encoding. So what exactly do we do in source encoding? Can anybody tell me? सोर्स कोडिंग में क्या करते हैं? सोर्स इनकोडिंग या कोडिंग में क्या करते हैं? एनीवन बताइए। वेदांत बताइए, आर्य आप बताइए, सोर्स इनकोडिंग में क्या करते हैं हम लोग? वनमाला, तुषार, मयूरेश, एनीवन? Are you there in the meeting or have you already left? Hello? Are you in the meeting? Okay.
Yes, sir.
So हाँ, तो क्या करते हैं हम लोग सोर्स इनकोडिंग में? बताइए मुझे. What is it that we do in source encoding? So we remove redundancy, okay? We remove something that is unnecessary. We simply want to represent our data as efficiently as possible. We want to save the space, okay? So we remove redundancy. Okay. And what we do in channel coding. So here you will see that we will be adding redundancy. Okay. Okay. I hope that it is clear to you. Okay. And how does adding redundancy increases immunity to the noise? That is what we have to see. And then we will see what are the different algorithms using which we can add redundancy to already existing code. Sorry. Just give me a minute. I will. Okay, sorry for that. So, as I was telling you that in error control coding or error correcting code or channel coding, what we do is that we add redundancy. Okay. And this added redundancy, which is generally called parity bits. So for example, our message bit is, let's say, just 2 bits. Okay. And then we have added 2 other bits as a parity bits. That is what redundancy is. Okay. Then how this added redundancy bit is going to provide immunity against any error that will occur through noise. Okay. That is something that is going to be study of this topic. And in channel decoding, what we will do is that with the help of extra added bit, we will be able to determine if there is going to be any error is there any error in the message? Okay. And if there is any error, can we correct that? Okay. So that is something. So this channel decoding is the process of error detection as well as correction. Okay. So most of the time there is error correction, and this is already defined by the protocol. So there are certain situation where we don't really need error correction. We simply know that there is going to be, whenever there will be error detection, source is again going to transmit the same message again. Okay. So that is where we don't really need error correction, but there are certain situations where we are going to need error detection as well, error correction as well. Okay. So we will understand how to use this extra redundant bit to actually do error correction as well as detection. Okay. And to give you an example of that, example of the same thing, let me just so this is going to be an example here, and what we have in this example is that we have a source. Okay. And this source has let's say 4 symbols. Okay. And let's assume that all symbols are equiprobable. So anyway, we are getting, let's say, the value, the source code. So this is 2-bit message that we will have. So we can have 00, we can have 01, we can have 10 and 11. So these are the 4 possible. This is efficient representation. So after source encoder, you will be getting these values, isn't it? 0001, 10 and 11. Okay. Is that clear to everyone? Now let's say that this is the same thing that you have transmitted. So you have, let's say, selected 00 and you have transmitted. Okay. And in the channel, so this is going to be our channel. So in the channel, there is some noise, and due to noise, what happens is that the second bit, which is already 0, is kind of changed. So it becomes 1. Okay, is that clear to everyone? Now you have your decoder. Okay, so you have your decoder. Will decoder be able? So decoder has this dictionary where it contains all these values. So it has 00. It has, it know that this must have been transmitted. This must have been means any one of these may have transmitted. Okay, 00, 10, 01 and 11. So it has this dictionary. So will this be able to determine कि there is an error here? ये बता पाएगा क्या कि is there any error or not? Decoder doesn't know what message has been transmitted. It only know what can be transmitted. Means either 00 may have transmitted, either 01 may have transmitted, either 10 may have transmitted, either 11 may have transmitted. For example, if it is English alphabet, that out of these 26 कोई भी A से Z तक कोई भी एक symbol transmit हुआ है. Okay. But if Z is converted to, let's say, Y, can this decoder be able to understand, okay, there is an error?
No.
No, right? So we will be not be able to. So in this situation, we will not be able to what? Understand that there is any what you can say error here. Okay. So no error detection in this situation. I hope this point is clear. Now let's take the same source. So I'm going to take this same source here. Okay. And what I will be doing is that I will apply source encoding now. Okay. So what I'm going to do is that I will apply source encoding. Okay. So in that step, what is going to happen is that so this source से आपका जा रहा है source encoder में, and this is a very simple kind of encoder which is just adding 1 or 2 redundant bit here. Okay. So this is source encoder here. So let me just try this. Sorry, it's error control coding. So we are adding redundancy here. So let me add redundancy. And we have decided that whatever message bit is, we are going to just add that only. Okay. So 0 0 है तो हम लोग क्या करेंगे 0 0 add कर देंगे. Okay. If we have 0 1, then we are going to add what 0 1. Okay. It is just arbitrary. I have decided. Okay. 1 0, then I have added again 1 0. If I have 1 1, then I have again added 1 1. And now we are transmitting. Okay. 0 0 0 0. Okay. And due to this channel, there is some noise. Okay. And because of this, this is channel and noise is added here. This may or may not be channel. It may be a storage medium or something like that. But with respect to communication, I would like to call this channel. And here the noise is added. And because of noise, let's say here we are changing only one bit. So let me change only one bit here. So noise is can affect any one of the bit, but we are restricting ourselves that there is, the probability of error and all that. Based on that, we know that only one bit is going to change. For example, there may be situation where there may be two bits are going to change. So we will see that about all those details later on. But for simplicity, let me assume that only one bit has changed. So I have changed the last bit. Okay. Okay. And we have this decoder. Okay. So we have this decoder. And it again has all these value, means it again has 0 0 0 0 in its dictionary, 0 1 0 1. It again has 1 0 1 0 and it again has 1 1 1 1. Okay. So will this be able to recognize that there is an error or not? Anyone?
Yes.
Yes, isn't it? Because 0 0 1 0 triple 0 1 it has received, and it know that it in its dictionary that is already provided to it, it knows that there isn't any what you can say symbol which is represented by triple 0 1. So there must be an error, isn't it? So it will be able to detect this error. Okay. So this is the simple example where you can see that just adding, let's say, two extra bit here in the message, we were able to get some sort of, uh, protection against the error, isn't it? We were able to detect that there was an error. Okay. So this is the concept behind error control coding. Okay. I hope that this part is very, very clear to you. Is this clear? So what will
Yes.
happen in error control coding? Error control coding में आपका क्या होता है?
So we can detect the error.
Okay, we can detect the error, but what actually we do? We have k
We
message
add.
bit. Okay, and from k message bit, we here add n minus k. And these bits are called parity bit. So whatever we are adding extra to the message bit, it's called parity bit. Okay. And based on that, we are determining n bit. Okay. And this n bit is going to be transmitted. Or it can be used for storage as well. So this is going to be transmitted and then it will provide some sort of protection. So the more elaborate method you will use to add this n minus k bit. Okay, for example, in the last one we have just used the repetition. Okay, so that wasn't a very good way of doing that. We will understand about all that later. But here you see that we added this and we were able to find it out. So what actually happened? Why it was able to detect this error? Okay. So let me just do this. So here we have 4 vectors. Okay. Here we had 4 vectors. Let's say example in message bit. So this is the message space. So message space, there were only 4 vectors that was possible in this space. And we have used all 4 of them. Okay. So if there was any error, so this is going to change to this one. So let's say this is A. So A will change to this either B or this C or this D. Okay. So A changed to B. We were not able to determine because this was part of the plane. But now when we added redundancy, what happens is that we have added 2-bit here in case you can see. So this is a 4-bit. So in 4-bit, how many vectors are possible? There is 2 to the power 4 vector possible, isn't it? Right? So total number of vectors that are possible here is 2 to the power 16. So we have 2 vectors here in this direction. Then we have 2 vectors possible here in this direction. Then we have 2 vectors possible here in this direction. Okay. And we have 2 vectors possible here in this direction. Okay, so how many vectors are there now? 3, 3, 2, 5, 3, 8. Okay, we have to add 4 more. Let me just add all of them. Okay, so this is now 10. Okay, and after 10 we will add, let's say, 2 more. So 10, 12, and then we have 14, and after that we are going to have 16. So total 16 message space is possible, and out of these we are using just 4. So let's say that we have used this one only, okay, and this one only, okay, and this one only, isn't it? And this one only, okay. Is this clear? Now this can change to this or this or this or this, isn't it? So there are still, you see that this can change to all these 16, isn't it? But chances, so here it was changing to B, C or D, isn't it? And the probability is 1 here that A is going to change to either B, C or D, isn't it? Now, but now A, and there is B, and there is C, and there is D. So A changes to B, C, D, its probability is reduced, isn't it? Here it was, uh, I mean, there are many. For example, A, कितने बच गए 15. So 1 is to 15. So 3 is to 15 chance है कि B, C or D में convert हो, isn't it? Are you getting my, when we have added this, so we somehow increased our sample, this vector space, and because of that, what is the advantage here is that the probability of A being means error detect ना हो उसकी probability क्या होगी बहुत कम है. यहाँ पे error detect होने की non होने की probability क्या थी 100%. And now that reduced to 3/15, isn't it? So this is what we do once we encoded space. So this is encoded space. Okay. And here what we are somehow doing that we are increasing the distance between A and B. So here the distance between A and B is very small. B and C is very small. C and D is very, and you will understand what we mean by distance. Okay. Don't worry about that. We will learn about what these means. And so distance means how many bit they differ. Okay. So here A differs from B in just 1 bit, isn't it? A differs in C in, let's say, 1 or 2 bit. A differs in D in 1 or bit or 2 bit, isn't it? Are you getting my 0 0 से 1 1 ये maximum distance है. तो maximum distance यहाँ क्या पे है, क्या है 2. But here 0 0 0 से 1 1 1 का distance क्या है, maximum distance? Now 4 you have. Okay, how many bits they differ? That is what going to be. We are going to use that as a distance, and that is called Hamming distance. We will have a all these definition later on. But for now, you have to kind of understand this, that we are somehow increasing the distance between these code vector. Okay, so I hope that this is very, very clear to you. Okay. So now let me just discuss what type of codes do we have. So this channel coding or ECC, the types is, there are 2 types of this. Let me just write this here. Okay. So error correcting codes are of two types. Okay. So the very first type is what is known as block code. Okay. And then we have the second type, which is known as convolutional code. Okay. So this block code again can be of two type. Okay. So we can have linear and we can have non-linear block codes. Okay. So we will have linear. Okay. Or we can have non-linear block code. Okay. So in our syllabus, we have only linear block code as well as convolutional code. So we have simple examples of convolutional code and simple examples of linear code. So linear block, and there is a type of linear block code that is known as, so there is a type of linear block code that is known as cyclic code. So you will see that cyclic code that we have to study is kind of an spatial part of this linear block code only. So it's a subset of linear block code. Okay. So I hope this is very, very clear to you. So what happens is block code is that block code mein kya hota hai? What happens in block code? Block code is that we will have k message bit. Okay. And we will utilize these k message bits only, k message bit only to add n minus k redundant bit or parity bit. And then we will get n total number of bits. So n bit, code word we will have. Is this clear? So we have k message bit and we have utilized only. So here, there, let me just write this. Only k message bits are used to determine these n minus k parity bits. Okay, so this is what we have in block code. Now in convolutional code, what happens is that, so in this you see that there is no memory, isn't it? It doesn't depend upon the previous k message. It doesn't depend upon the future k message. But whereas in convolutional code, the whole thing is kind of same. We will have k message bits. And this k message bits, we are going to add n minus k, and let me not write add. From this, we are going to produce directly using some mechanism. Okay. N bit code word. Okay, code word. Now this n bit code word that is being generated depends not only on the current k message bits, but also on the previous m, let me just use this m here, m message bits. So in some way it has memory. So what happens in linear block code? A block code is that the 000 से, let's say आपने 2 bit add करके 00 add कर रहे हैं, right? So 50 आप बना रहे हैं and that is always going to be there. Okay, 000 हमेशा रिजल्ट क्या होगा, 5 जीरो आपको देगा ब्लॉक कोड में. लेकिन कन्वोल्यूशनल कोड में डिपेंडिंग अपॉन द स्टेट ऑफ द मशीन, okay, 000 may result in 00050, it may result in 00010, it may result in 11101. So depending on what is going to be your state of that message, you know, that machine, convolutional code is going to give you different n bits every time. Is this clear? So in some way it has memory and block code doesn't have memory. Okay. So I hope that it is very, very clear to you. सबको समझ में आ रहा है कि क्या डिफरेंस है ब्लॉक कोड और कन्वोल्यूशनल कोड में? At least
So can you
on the
repeat the?
server. Let me just repeat it like this, that block code what happens is that आपका 000 जो है वो हमेशा क्या होगा, जो भी मैसेज आप n माइनस के पेरिटी बिट ऐड कर रहे हैं, टोटल n बिट बन रहा है उसकी वजह से. So जो n minus k parity bits है, that is generated using these k message bits only, and your algorithm is constant. So every time you will feed the same k bits, you will get the same n bits. Okay, but in convolutional code, what happens is that the n bit that is generated as the code word, this does not only depends upon the k message bits, but it also depends upon the previous m message bits. So k message bit सभी आया, उससे पहले कुछ और आया होगा मान लो. So whatever is the memory of this convolutional encoder, depending upon that, and what is that stage means क्या वो previous words है, उसके वजह से आपका जो n bits that is being generated, that can change. Okay, is this clear?
Yes.
So that is why convolutional code is somehow more robust, and I mean it's actually much better, but still they both have their relative advantage and disadvantage. And one of the another advantage of convolutional code is that um, this k and n are relatively very small as compared to this n minus k block code. Okay, to achieve the same error correction and detection capability. So for example, आपको अगर दो 3 error detection and correction technique बनाना है, तो आपको like 15,5 का कोड वर्ड बनाना पड़ेगा. लेकिन फॉर एग्जांपल इन कन्वोल्यूशन कोड 5,10 पे ही वो काम चल जाएगा, डिपेंडिंग अपॉन व्हाट इज योर मेमोरी. ओके, so in that some way convolutional codes are much more superior, and they are faster as well, because relatively they are going to process less number of bit at a time. Okay, so that's why convolutional codes are faster than block codes. They are superior in terms of error detection and correction techniques. But even given all these things, still block codes are used in different situations. They have their relative advantage in certain situations. So we will see about all that later in this lecture. Okay. So this is what we have in terms of block codes, and we have in terms of convolutional code. Okay. So now we are going to discuss about something what is called as linear block code. So we will discuss this topic, that is linear block code. Okay, and what we mean by linear, we will understand here. Okay. So what is block code? We have k input, k bit as input to block code, isn't it? And this block code encoder gives us n bit, isn't it? So let me just type this block code encoder. This is encoder actually. So this will give us how many? N bit. So it takes k bit as input and gives n bit as output. This is what your block code is. So we are taking a block of bits and we are giving you block of bit. Okay, that is why it's called block code. Okay, now what happens in linear block code is that. So let me define this. Okay. Okay. So definition of linear block code. And this says that and n comma k. So k is your message bits and n is going to be your code word bits. Okay, so k आपने दिया और n मिल रहा है. So here n is greater than k. Let me just uh, write this here. Block code, and let me under bracket write this n is greater than k if it is not already clear. Okay. Is n comma k block code is n is a should be a is a linear block code if v1 comma v2 is element of C, okay, where C is your code word, okay, then v1 v2, so this is XOR v2 is also element of C. Okay, तो कोड वर्ड क्या है कि अगर आप किसी भी दो लीनियर ब्लॉक कोड क्या है, जब आप किसी भी दो कोडवर्ड को ऐड करेंगे तो आपको क्या मिलेगा, तीसरा जो मिलेगा जो भी रिजल्टेंट होगा दैट शुड आल्सो बी पार्ट ऑफ दैट कोडवर्ड ओनली. ओके, and this is what we are going to see here in example. Okay, and once we will see how to generate this and all that, it will become very clear to you. Okay, so to generate now to generate this linear block code, there are many what you can say minor things here that I'm skipping over. That is something that you are not going to require. Okay, but I'm just going to discuss about this generator matrix. Okay, so generator matrix is a matrix that is used to give us this n vector from this k word. Okay, so it is basically a matrix. Okay, and what is generally the shape of this? So G is generally defined as, in two ways we can define it. So it is given as P. Okay, so P is going to be a matrix that will generate the parity, and then it is P. Let me just write this semicolon IK. Okay, means P or IK है आपका साथ में. Okay, IK is basically a K by K identity matrix, or this G may be like this, that you have IK first, okay, and then you will have this parity bit matrix. Okay, and you will learn what we mean by this, okay, very soon. So in this way what will happen is that जो आपके मैसेज बिट्स हैं वो बाद में आएंगे, पैरिटी बिट्स पहले आएंगे. यहाँ पे क्या है, मैसेज बिट पहले आ रहा है और पैरिटी बिट्स बाद में आ रहा है. सो इन एनी वन ऑफ दीज टू वे योर जनरेटर मैट्रिक्स विल बी गिवन. ओके, एंड वी जनरेट आवर कोड वर्ड. तो कोड वर्ड जनरेशन के लिए क्या है, so code word is basically C, and this C is generated M times G. M और G को multiply करने से करके. Okay. Now you will have to understand that this multiplication or addition, multiply करेंगे आप matrix को. I mean M is a vector, isn't it? And G is also going to be G is a matrix. So you are basically multiplying a vector, pre-multiplying a matrix by a vector. So we are in matrix multiplication. आप देखते हैं multiply भी करते हैं हम लोग, add भी करते हैं. So all the operations are performed. So just one caution that all operations are performed on GF, Galvez filled 2, GF2. Okay, and what does that mean? It means that हम लोग modulo 2 operation करेंगे. Okay, basic meaning यही है. I mean, even if you don't know anything about field and all these things, though I have already shared those video lectures. So even if you don't know, all you have to know that what you are going to do, you are going to perform modulo 2 operation, isn't it? And what is modulo 2 operation? So let me just discuss this modulo 2 operations now so that you understand this, how to get this to operation. So I think you are already familiar with this. So in GF2 what will have? The GF2 में आपके सिर्फ दो ही symbol है, 0 and 1. Okay. What we have only two symbols. So let me define this modulo 2. What will happen is that when anything, if you are multiplying with anything, that has to be between 0 and 1. So if you get, let's say, for example, you are doing normal arithmetic multiplication and addition, and you somehow get 3. It means what you have to do, आपको 2 से divide करने पड़ेगा, जो भी remainder है वो लिखना पड़ेगा. I will not discuss this. I will just verbally tell you what to do here. Okay, so what we will do is that we will get the result by dividing it by 2. Whatever is that, we will follow the normal arithmetic. Okay, and whatever is the value that we will get, we will simply divide it by 2, and whatever is the remainder, that is going to be, that is what we will write. Okay, so let's say, for example, if we got 4, then what is going to be the result of modulo 2?
0.
0. Isn't it? You will divide it by 2 and you will see that it's either going to be 0 and 1 if you divide something by 0. So that is something that you will have to do now. Okay. So again, this linear block code can be of two types. One is systematic, another is non-systematic. So the generator matrix form that I have given you is basically systematic. What we mean by systematic? In systematic code word, you will be able to identify your message bit. They are given as a chunk only, isn't it? But in non-systematic code word, this is entirely different. Whatever is your message, you will generate something else. Okay, so that is something that is we are not going to prefer. We are going to use systematic code word from here only. So let me just give you a message bit, a parity bit, and then you will have to determine based on that. Okay, all the code word. So let's say that P parity matrix is given as let's say 1 1 0, and then after that we have 1 0 1, and then after we have 1. Okay, for a six comma 3 linear block code. Okay, so this is something that has been given, and from this we will get our generator matrix by this formula. So what is n here? So you can see that n here is equal to 6, k here is equal to 3. So what is going to be g? G generally we will write as ik semicolon p. So we will first write our message bit. Okay, so what is going to be our message bit here in this case? You can see. So message अगर G मैट्रिक्स देखें तो I के मतलब क्या हुआ 1 0 0 0 1 0 and then 0 0 1. So this is IK, and what is your P? P is going to be 1 1 1, then 1 0 1, and after that we have 1 0 1 1. Okay, so this is going to be your generator matrix. And let's say we have to calculate all the code words. Okay, so message bit is 3-bit, right? So message is 3-bit, isn't it? What does that mean? What can be our message? Message can be 0 0 0, isn't it? Message can be 0 0 1. It can be 0 1 0. It can be 0 1 1. It can be 1 0 0. So on and so forth, isn't it? Can you see this? Is this clear? And now let's say that we have to calculate this code word. So if I'm going to use only one of this, so this can be all these things, but let me use for m is equal to 0, 0, 1. What is going to be the code word? Okay, so C can be calculated by m times G, isn't it? So what is m? M is 0, 0, 1. And what is G here? What is G? 1, 0, 0, 0, 1, 0, 0, 1. And then that is multi after उसके बाद क्या है 1, 1, 1, 1, 0, 1 और 0, 1, 1. So you see when you multiply this with this, so पहले ये मैट्रिक्स में मल्टीप्लाई करने से क्या मिलेगा आपको 0, 0, 1 ही मिलेगा. So you will get 0, 0, 1 और यहाँ पे मल्टीप्लाई किया इसमें तो क्या मिला 0, 0, 1 को मल्टीप्लाई किया इससे तो it will result in 0. So 0, 0, 1 is multiplied in this column. So what you will be getting? You will be getting 1. And when 0, 0, 1 is again multiplied in this last column, you will be getting 1 only. So this is going to be the code word with respect to this. Okay. So in general, G is given, and based on that, you will have to compute this, or parity matrix is given. Based on that, you will have to create a generator matrix, and then by multiplying this, you will be getting your parity bit matrix. Okay, let me just give you another example. So let's say if
Excuse me, sir.
mass is, हाँ बोलिए.
So we are getting m by doing n minus k ना.
क्या कर रहे हैं मैं समझा नहीं.
How we are getting m by doing m?
M
I mean n minus k ना.
message bit is generally predefined. Okay. So message bit is क्या है आपका कि कुछ भी हो सकता है 3 बिट का कोई भी बिट हो सकता है समझिए कोई भी कॉम्बिनेशन यानी 0, 0, 0 से 1, 1, 1 के बीच में कुछ भी हो सकता है. Okay, out of that I have decided to take this 0, 0, 1 only. Okay, is that clear
Okay, sir.
to you? Okay, so 3 बिट का मैसेज है मतलब वो क्या है सारे पॉसिबल होंगे कॉम्बिनेशन. Is that clear?
Yes, sir.
Okay, so similarly what will happen is that for m, let's say if message bit is let's say your 111, okay, what is going to be C? Can you determine C by multiplying with mg? Can you give me this value, everyone?
Sir, is it 1, 1, 1, 0, 1, 1?
0, 1, 1 यही होगा. You're sure? Okay, so let's determine C using the same formula that we will multiply with m times G, isn't it? What is m? M is 1, 1, 1, isn't it? This is our message bit, and we will multiply this with our generator matrix. So what is our generator matrix? We have 1, 0, 0, and then what we have 0, 1, 0, and then we have 0, 0, 1. So this is basically identity matrix, isn't it? Multiplying anything with the identity matrix results in that only. So that we already know, and that's why it is systematic. So 0, 0, 1 was here. You say that 0, 0, 1 is also here at the starting. So after that, what we have is 1, and then 1, and this is 0, and after that we have 1 and 0, and then we have 1, and then after that we have 1, 1, and 1. Okay, so if you multiply this with this, so first 3 bits are going to be the same. We already know. Wherever अगर पहले 3 आइडेंटिटी है तो पहले 3 मैसेज हो जाएगा. अगर ये आखिरी में रहते तो ये आखिरी में 3 हो जाता है. It's very simple, isn't it? Now, what is going to be your this parity bits? So these are our message bits only. What is n minus k parity bits? So that is going 111 को multiply करेंगे इसमें, right? So 111 multiplied with 110 will result in 1 plus 1 2, isn't it? इसको अगर हम यहां से इससे मल्टीप्लाई करें, लेट मी जस्ट हाईलाइट दिस, इफ यू मल्टीप्लाई दिस विद दिस हियर, व्हाट इज इट दैट यू विल बी गेटिंग? क्या मिलेगा आपको, बताइए एवरीवन.
So 2.
2. But it, as I told you, this is in Galvez fill 2. It means it is modulo 2. 2 मिला तो 2 modulo 2 मिला. 2 आपका रिजल्ट है, बट 2 को क्या लिखेंगे? 2 modulo 2. इसका मतलब क्या हुआ? 2 divided by 2 or whatever is the remainder. So this is basically means remainder of whatever you are getting. So 2 divided by 2. What is remainder of 2 by 2?
0.
0.
Right? So did you get this? I mean, it's very simple, isn't it? So ये वैल्यू कितना होगा हमारा? 0. Is that clear, everyone? Now let's say we are multiplying the same thing with the next column, that is this 101. इसको नहीं, मैं दूसरा कलर यूज करता हूँ. This is better. We are multiplying this with 101. What will happen? क्या मिलेगा आपको? 111 को 101 से मल्टीप्लाई करेंगे तो
Again 0.
सॉरी, वो मेरा नेट जो है कंप्यूटर मेरा शट डाउन हो गया था, इसकी वजह से मेरा जो नोट्स है वो चला गया. ओके, So anyway, is this visible to you? Let me just try that again. Again, the same problem. So our message bit was equal to how much? क्या था? What was our message bit? 111, right?
One.
Sorry, it was triple
Yes.
one, isn't it? And the generator matrix that we had was this. Sorry, let me just write this again. 101, then 011, and then 0. So this is 011. So this is first part is identity, and in the second part we had our parity, and parity bits were given by what were the parity bits? I think 110 here, and then 101 here,
Then
and then triple
one.
one, right? So we were trying to get what
Yes.
the value of this code word is. So m times g we were doing, and m is, let's say, 1. Let me make this a bit bigger. So 1 1 and 1. So this is our masses, and the generator matrix that we have, let me just write that again. So generator matrix was 1 0 0, then we have 0 1 0, and then after that we had 0 0 1, right? So first part is identity, second part is going to be your parity bits. So 1 1 0, and then we have 1 0 1, and then 1 1 1. Sorry, so let me make this in a matrix form. Okay, very good. I can switch back to normal size. Okay, just wanted to identify these. Okay, so when you multiply with this part, the resultant first 3 bits are going to be the same as message bits, isn't it? So it will be triple one only, isn't it? Right? And when we will multiply this with this, what is it that we got? We got 2, right? Triple one को 1
Zero.
1 0 से करेंगे तो 2 मिला. 1 into 1 1, 1 into 1 1, and then we have 1 into 0 0. So हमें 2 मिला. So 2 in modulo 2 is going to become 0, isn't it? Then after that we multiply this part with let me highlight this one here. So we multiplied this with 110, and what is going to be the resultant of when you will multiply with this one?
Again 0.
It's again going to be 2, and 2 will be equal to 0, isn't it? So it will be again 0. So let me make this with some green color. Yellow actually proper दिखता नहीं है, so otherwise I would have used arrow yellow. Let me use yellow only. I mean, I hope that it is kind of visible to you. Make it back to this green only. Okay. So 110 ये मिला ये. अब ये मुझे 111 को अगर 111 से मल्टीप्लाई करेंगे तो क्या मिलेगा हमें बताइए?
1.
1.
Right? If you multiply this, you will be getting what? You will get 3, and
3
3
modulo.
divided by 2 will be equal to 1 only, right? Isn't it? So that is going to be 1. Okay, red में करना था. So I hope how to get these code word is at least clear to all of you. Is it clear or not?
Yes, sir.
Okay, so there is a 100% chance that you will get a question like this. Okay, they will give you a generator matrix, and they will give you a message bit, and they will ask you what is going to be your code word. Is this clear?
Sir, can you explain last 3 bits again?
Last 3 bits again. So whatever operation we are doing in Galvez field 2. Okay. So Galvez field, I mean, that's a different discussion. I'm not going into that because that will take the complete lecture. So you have to understand that every result that you are getting in normal arithmetic, if you have to convert it to Galvez field, what you have to do, you have to do modulo 2 over that. Okay. सो 111 को हमने मल्टीप्लाई किया 110 से, तो हमारा डेसिमल में क्या मिलेगा ये बताइए? 111 को 110 से मल्टीप्लाई किया तो आपको क्या मिलेगा?
So 2.
2, राइट? और 2 का मॉडुलो 2 निकालेंगे, मतलब 2 को डिवाइड करेंगे 2 से और रिमाइंडर देखेंगे कि कितना है. तो 2 को 2 से डिवाइड करोगे तो रिमाइंडर कितना आएगा?
0.
0, right? So that's why you got here 0. ये क्या मिला आपको? 0 मिला ये bit. Is this clear? Now you multiply 111 with 101. Again you got 2, and 2 in modulo 2 will become 0. Isn't it? Right? फिर 111 को आपने मल्टीप्लाई किया 111 से, तो आपको क्या मिलेगा? 3 मिलेगा डेसिमल में, isn't it? 1 into 1, 1 into 1, 1 into 1, isn't it? So you will get 3. Is that clear?
Yes, sir.
So 3 को मॉडुलो 2 करोगे तो रिमाइंडर कितना होगा? 2 से डिवाइड करोगे तो रिमाइंडर कितना होगा?
1.
1. So you got 1 here. As you can see, आपको क्या मिल रहा है यहाँ पे? You got 1 here, isn't it? So is the last 3 bits clear to you?
Yes, sir.
Okay, so just remember that every operation that we are performing from here onwards, इस यूनिट में सिर्फ मॉडुलो 2 करना है. ठीक है? Fortunately we don't have RS code and Gole code, otherwise मॉडुलो 2 से हमारा काम नहीं चलता. But यहाँ पे हमारा for all these code, linear block code, cyclic code, even for convolutional code, modulo 2 additions, modulo 2 addition, modulo 2 multiplication means whatever is the result in decimal, you have to do divide that by 2 and find out the remainder. Okay? और in simplest word, XOR कर रहे हैं. XOR में क्या होता है? What is XOR? XORing भी पढ़ा. So this is modulo 2 means XORing kind of. Is that clear?
Yes, sir.
Okay. So अगर आपके पास इवन नंबर ऑफ बिट्स होंगे तो वो क्या होगा? 0. ऑड नंबर ऑफ बिट्स होंगे तो क्या होगा? इवन नंबर ऑफ 1 मतलब 1, सॉरी 0. ऑड नंबर ऑफ 1 मतलब 1. एक्सॉर में यही होता है ना? So that is what is happening here.
Yes.
Okay, so I mean the way you are going to understand, that's fine. I'm not going to insist on that, and that is going to be okay for linear block code as well as cyclic code. So this is what we got. Now let me give you a question, and that is something that you can try and solve. Okay. So I will go give you a question that is something that I will be using it for a while. So let me just give you that. So we have, so let me write this. Consider a systematic seven comma 4 linear block code. So it is always abbreviated as LBC. Rarely people write it linear block code. Okay, LBC, whose parity bits are sorry. This is generally, we call this parity check bits. So let me just write this. Or parity bits doesn't matter. Parity check bits are given as so let me write this. V4 is equal to U1. So this will either be written as plus or this, like this is the meaning of XOR, isn't it? Or this is the meaning, either they will write plus or they will plus के ऊपर गोला लगा देंगे. Okay, so both of them are quite popular. Okay, so U1 plus U2 plus U3, V4 is equal to this, V5 is equal to U1. Sorry, let me write U0 plus u1 plus u2, and then v6 will be given as u0 plus u1 plus u3. Okay. So this is v4, v5, and v6 is given. Okay. So you see that this is going to be, so let me just write this. What is the meaning of these symbols? So u1, u2, u3, u4, all the way up to u3 only. So u1 is u0, u1, u2, u3. These are the message bits. So let me write this. So message bits क्या है हमारा यहाँ पे? What is the meaning of symbol? I will just try to describe this. So u0, this is going to be u1, and this is going to be u2, and this is going to be u3. Is that clear? And what is going to be your code word? So code word is generally given as, code word में हम लोग जो symbol use करते हैं वो v use करते हैं. So v0, first one, second one is going to be v1, then v2, and v3, and v4, and v5, and v6. तो total 7 हो गया 0 से लेकर 6 तक. Is that clear? Is this clear?
But sir, V3 V0 to V3 is not given, no?
v0 to v3 is not given, you are saying here. So this is
Yes, sir.
what let me just explain that. So here it is given as this is a systematic code word. Okay. What does that mean? It means that is what I'm going to write this here. Let me write this here only. So here in this case, what happens is that v0 is going to be equal to how much? u0. v1 is going to be equal to how much? u1. v2 is going to be equal to u2, and v3 is going to be equal to u3. So this is for systematic code word. Is this clear?
Yes, sir.
So systematic में क्या होता है? अभी क्या होता है आपका? You will multiply m with g. Isn't it? G में क्या होता है? पहले identity matrix होते हैं, यानी ये हो गया. So let me just convert this whatever is given to the matrix first. Okay. Is this? I was just explaining the meaning of the symbol. Okay, and let me give. So from here, let me try to get our parity matrix. So what is going to be parity matrix? आपका क्या है? u1 दिया है, u0 नहीं है यहाँ पे. v4 में क्या है? u1, u2, u3, isn't it? यानी पहला क्या हो गया? वो 0. समझ में आया? u1, u0 किससे मल्टीप्लाई हुआ है? 0 से. So I can write here like this: 0 times u0, isn't it? Here I can write what? u0 दिया है, u1 दिया है, u2. 0 times u3, and I can write here what? 0 times, I mean 4 नहीं है, 3 ही है, right? So ये u1, u2. So u2 is multiplied with 0. So now you can understand here. So what is going to be your parity matrix? The v4 is equal to, fourth position क्या है? 0, and then क्या है? 1, और उसके बाद क्या है? 1, उसके बाद क्या है? 1, right? u5 क्या है? u1 is equal to, u0 is equal to 1, so this is 1. u1 is there, so this is also 1. u2 is there, that is also 1. u3 is not there, it means it is 0. Similarly v6 में क्या है आपका? 1. This is going to be what? 1, and this is going to be what? u2 is 0, so this is 0, and u3 is 1. So इक्वेशन से आपको पेरिटी मैट्रिक्स करने समझ में आया कि नहीं?
Yes, sir.
Okay, very good. So we got our parity matrix. So what is going to be the generator matrix now? Generator matrix, we already know that it is I, K, colon parity matrix. क्या होता है? I K colon parity matrix या P colon parity matrix. But P is given in terms of V5, V6, V4, V5 and V6. It means it's last in the last only, isn't it? So that's why I have written it. अगर यहाँ पे ये V4, V5, V6 की जगह V0, V1, V2 दिया होता, and U1, U2, U3, this is always be given in terms of U1, U2, U3 only, then we will understand that parity matrix in the beginning only. P, IK है generator matrix का form. Is that clear? Is it clear to all of you?
Yes, sir.
Okay. So this is now given. Okay. So what is going to be the parity matrix? Can anybody tell me? So first is IK. It means it is 1, 0, 0, 0 पहले, और उसके बाद क्या होगा 0, 1, उसके बाद क्या होगा ये 0 और ये भी 0, उसके बाद क्या होगा 0, यहाँ से क्या होगा ये 0, आइडेंटिटी मैट्रिक्स है ना ये पार्ट, 4x4 identity matrix. Message bit is 4, isn't it? Is this clear to everyone?
Yes, sir.
अब इसके बाद हमारा क्या आ रहा है जनरेटर पार्ट. So generator part I'm going to write this in green. So what that was equal to 0, 111, 111, 0. So this was 0 and then 1, 1, 1 and then 111, 0 और उसके बाद क्या है 1101, right? So then after that we have 1 and 1 and then 0 and then 1. Is that clear? So this is going to be our generator matrix now. Is it clear to everyone?
Yes, sir. Yes.
Now for this generator matrix, determine all code word. Determine all code word. That is the question. Okay. So it means we have to find all message bits. So what is going to be our message bits? Message bits are 4-bit, isn't it? N कितना दिया, K कितना दिया है यहाँ पे 4, 7,4 कोड वर्ड दिया है ना आपका. Can you say this? You have been given 7,4 code words. यानी message bit कितना है N, K, right? So K is equal to 4. It means message bits are 4-bit. So how many possible bits will be there? Possible messages will be there 0, 0, 0, right? उसके बाद क्या होगा आपका 0, 0, 0, 1. उसके बाद क्या होगा आपका 0, 0. Sorry, this is going to be 1, 0. उसके बाद क्या होगा आपका बताइए 1, 1, isn't it? Then
0.
what you are going to have 0, 1, 0, 0. You will have 0, 1, 0, 1. And then after that what you will be having 0, 1, 1, 0 and 0, 1, 1, 1. यही होगा ना. उसके बाद क्या होगा 1 से स्टार्ट होगा, राइट? 1, then you will have 0, 0, 0, then you will have 1, 0, 0, 1, and I mean there will be total 16. So let me just write that. We have to calculate for every one of them. I will visit this problem again and again. Okay. So 1, and what you are going to have here is 1, 0, 1, 0, and then what you have 1, 0, 1, 1, and then after that 1, 1, 0, 0, right? And then you will be having 1, 1, 0, 1, then 1, 1, 1, 0, and then 1, 1, 1, 1. Right? Total 16, isn't it? So
So
this
we
is
have to calculate for the
all of them. So 0, this is for decimal 1, this is for decimal 2, this is for decimal 3, this is for the decimal 4, this is for decimal 5, isn't it? Are you getting my point? Decimal 6, decimal 7, decimal 8, decimal 9, isn't it? Decimal 10, 11, 12, 13, 14 and 15. What we have to discuss later, we need to find out all code words here, okay? And that's why I have given this. Okay, this is the bit. So इसके लिए C क्या होगा? That is what I want you to calculate. So given this code generator matrix, that we have already determined, okay, based on whatever the parity bit is given to us. Can you calculate 0 0 के लिए क्या होगा? If all these bits are 0, what is going to be the code word? Can anybody tell me?
So 0.
70.
It will be 70, isn't it? So let me write this. मुझे कोई और color में लिखने दो. Let me write this in blue, okay? So this is 0, 0, 0 and 0. And last 3 जो है वो मैं कोई और color में लिखता हूँ. So let me use this pink color. 0, 0. So these 3 are going to signify our parity bits. अभी 0 0 1 के लिए क्या होगा बता सकते हैं आप मुझे? One thing that we are sure that first 4 bit are going to be 0 0 0, whatever our message bit is. Can you be sure about that? Because first we are multiplying with identity matrix, isn't it? The first part is identity. Can you see this? ये आपका part जो है, this part here is identity, isn't it? This is a identity matrix. Can you see this? So this is IK and this is P. Parity matrix, isn't it? So IK से multiply जब हो रहा है आपका bit, so you will get the same bit, isn't it? Identity से multiply करने से क्या होता है? इसीलिए तो इसको हम लोग identity matrix बोलते हैं ना? Hello?
Yes, sir.
And if you multiply with 0 0 0 1, what will happen? 0 0 0 1 से multiply करेंगे, 0 0 0 1 से multiply करेंगे, 0 0 1 से. Can you see that you are selecting this fourth one only?
All will be 1.
All will be not, no, not all will be 1. Only this 101 you will be getting. So if you do this, you will get 101, but please do that. Okay. So अगर आपने 0001 से multiply किया 01110 को तो आपको 1 मिलेगा, right? You will get what? 1. And then दूसरे column में ये मतलब like this is your sixth column. Sixth column में multiply कीजिएगा. So what is it that you will be getting? 0. ये कितना मिलेगा? 1 मिलेगा. Is this clear? When you are going to multiply with this one, what is it that you will be getting? You will get first 4 bit as the same as message bit. So 0, 0. Then what you will have 1. और उसके बाद क्या मिला आपको 0. और 0 0 1 0 से अगर आप multiply करेंगे इसको तो आपको क्या मिलेगा?
So 1 1 0.
1 1 0, right? Very good. So you got this. So we'll get 1 1 0. So 0 0 1 0 मतलब ये 4 जो रो है यहाँ पे देखो ये 4 रो जो है क्या रो मिल रहा है हमको ये 0 0 1 0 सॉरी 4 रो आपको दिख रहे हैं यहाँ पे. Let me highlight this again. So you have this as first row. This is the second row. This is the third row, and this is the fourth row. Isn't it? So when you are multiplying it with 0 0 0 1, then you are selecting only fourth row, isn't it? Can you see? बाकी रो को आप क्या कर रहे हैं? 0 से मल्टीप्लाई कर रहे हैं. फोर्थ रो को 1 से मल्टीप्लाई कर रहे हैं, isn't it? जब 0 0 1 0 से मल्टीप्लाई कर रहे हैं तो आप क्या कर रहे हैं? पहला नहीं ले रहे हैं, दूसरा नहीं ले रहे हैं, तीसरा रो ले रहे हैं और चौथा रो फिर से नहीं ले रहे हैं, तो तीसरा रो आ गया. ऐसे ही आपने 0 0 1 0 को मल्टीप्लाई किया. सो यू आर बेसिकली फर्स्ट दो को तो 0 से मल्टीप्लाई किया, इन दोनों को ऐड कर रहे हैं, isn't it? So 1 1 कितना मिलेगा आपको? 1 1 2 and 2 will become how much? What will be 2? 1 1 को ऐड किया आपने तो क्या मिलेगा आपको? So this part here you will be getting at 0 0 1 1 only. Can you see this that you are getting 0 0 1 1 only? Right? और लास्ट 3 क्या मिलेगा? इसमें हमने लास्ट के दो रो को ऐड कर दिया बिकॉज दिस इज 1 1, राइट? तो लास्ट दो रो को हम लोग ऐड कर रहे हैं, यानी 110 को और 101 को। तो 11 कितना होगा? वी विल गेट हाउ मच? 112 and 2 modulo is 0, isn't it? So this is going to be 0. And this part is going to be how much? 10. So this will be 1. And this is 0, 1. This is again going to be 1. You can do this and you will find the same thing. Can you do, और जैसे भी आपको अच्छा लगे वैसे करके मुझे सारे के सारे बिट बताइए। तो what is going to be the fourth bit? Have you taken note of this? आपने नोट ले लिया है ये पेरिटी मैट्रिक्स को, सॉरी जी जनरेटर मैट्रिक्स को आपने कॉपी कर लिया है? Hello? Am I audible?
Yes, sir.
If you have copied it, then आपको क्या है, आपको मल्टीप्लाई करना है और बताना है मुझे. So he is going to tell me the fourth bit. This 00100 से मल्टीप्लाई करेंगे जनरेटर मैट्रिक्स को, क्या मिलेगा? मंदर आप बताएंगे?
सर 01001111
00111
सर
मिलेगा.
01010011
So we will get 0100 and then we should get 111. You are saying, let me just see. Yes, you will get 111. So let me just write that. So we got 111, isn't it? This is. अभी पांचवा कौन बताएगा मुझे? Who is going to tell me? Subham, are you going to tell me?
Yes, one.
Okay, तो फिफ्थ वन क्या मिलेगा हमें बताइए? तो शुभम, शुभम कहाँ गए आप? Are you there in the meeting?
0101.
Okay, 0101 और उसके बाद
Sir, 010101
01
and 1.
1. So लास्ट वाले 011 मिलेंगे आप बोल रहे हैं ना? तो मुझे देखने दो.
Yes.
01 ये 0 हुआ, ये 1 हुआ और ये फिर से 0 हुआ. तो ये तो 0 होना चाहिए ना लास्ट वाला?
Last वाला will be 0.
लास्ट वाला 0 है. So
Yes,
this
sir.
is going to be 0, this is going to be 1. Okay, and this
0.
is going to be 0. I hope that this is clear to you. सिक्स्थ वाला कौन मिलेगा मुझे बताएगा? Who is going to tell me? Is Tanya, are you there in the meeting? Let me see. Who should tell me? वरद आप बताइए. वरद, are you there in the meeting? सिक्स्थ जो है 0110 को अगर जनरेटर मैट्रिक्स से मल्टीप्लाई करेंगे तो हमें क्या मिलेगा? What is it that you will get? Hello? Varad, are you there in the meeting? मयूरेश आप बताइए.
So 0110
0110
001.
and then we will get 001 you are saying. Let me write this 001 and let me verify this. 0110 001 001. Very good. 001. So we will, now I'm going to write this in green. Sorry, this pink or whatever color is this. Okay. Very good. Next कौन बताएगा मुझे? Who is going to tell me now? आर्या आप बताइए. आर्या, are you there in the meeting? वेदांत आप बताइए क्या होगा? वेदांत are you there in the meeting? If you multiply 0 triple 1 with the generator matrix, what is it that you will be getting? Hello?
Sir, can I?
Yes, please.
So 0 1 1 1 1 0 0.
0 1 1 1 and then you are saying that 1 0 0.
Yes, sir.
1 0 0. Let me verify this. ट्रिपल 1 मतलब लास्ट के 3 रो को मुझे ऐड करना है, तो 1 0 and 0. वेरी गुड, वेरी गुड. एनीवन एल्स? एट्थ का क्या होगा बता सकते हैं मुझे?
So 1 0 0 triple 1.
0, then you are saying triple 1, right? So let me
Yes,
just,
sir.
this is perfect. Okay, 1 0 0. What about triple 1? Let me see if the first row is triple 1. First row is 0 1 1, right? So it should not be triple 1. It should actually be 0 1 1. You see 1 0 0 से मल्टीप्लाई कर रहे हैं, यानी फर्स्ट रो ले रहे हैं और लास्ट के 3 रो को हम ले नहीं रहे हैं, यानी दिस पार्ट, लास्ट 3 पार्ट शुड बी इक्वल टू द फर्स्ट रो ओनली. ओके, so first row क्या आ रहा है आपका? 0 1 1 only, isn't it? So you will be getting 0 1 1. Is this clear?
Yes, sir.
Okay, you can do that calculation and you will end up with this result only. Okay. Is this clear to everyone? Okay. Similarly for this part 1 0 0 1, that is 9. क्या मिलेगा हमें? 1 0 0 1, right? That is there. And after that last
1
4 digits क्या मिलेगा हमें?
1 1 0.
1 1 0.
1
So let 1 1 0. Is that correct?
Yes, sir.
Let me see. We are adding first and last, right? So 1 1 and 0. Very good. Similarly for this one 10, that is 1 0 1 0. क्या मिलेगा हमें? So we'll
So
get
1
1
0 1 0
0
1 0 0
0 और उसके बाद क्या मिलेगा हमें?
1 0 0.
1 0 0. So I hope that you are correct. I'm not going to check this again. Next one is,
So 1 0 1 1
so
0
next
0
one is
1
going to 1 0
1 1
1 1, then
0 0 1.
0 0 1. Okay. Next up, what you will be having? 1 1 0 0, right? And last 3 bits. So let
1 0 0.
this will be 1 0 0. Okay. Next up we have this 1 1 0 1 और इसके लिए क्या मिलेगा आपको?
0 0 1.
0 0 1. And then we have next part, that is triple 1 0 और आपको लास्ट के 3 बिट क्या मिलेंगे?
0 1 0.
0 1 0. Okay. Next up we have 4 1, right? So we will get this as 4 1 only. 1 1 1 1. And what will be the last 3 bit?
So all are 1.
All are 1. Are you sure? Now there is one unique feature here, that in linear block code, for there will be always a all 0 code word, right? Can you say this, that we are getting first when you have 0 0 0, your code word is all 0, isn't it? So in a linear block code, this is something that you should write, okay? That in a linear block code, you will be always be getting a all 0 code word. Okay, there are some definition that we are going to see, and then after that we will discuss this. Okay. So let me discuss the very first thing that I will be discussing is actually decoding. Okay. So decoding se pehle let me just discuss something that should be. So there are something that you should know. So let me discuss those definitions. So there is very first thing is that is called Hamming distance. Hamming हो गया है, Hamming है, HAMMING distance. Okay. And between any two code word, दो code word दिए हैं C1 and C2. Okay. So this is defined as number of bits in which they differ. So let's say C1 is given as 1001 and C2 is given as 0111. Okay. So what is going to be distance between C1 and C2? What is going to be Hamming distance here? Can anybody tell me? Based on the definition?
Sir, 3.
3 होगा. कंफर्म है आप? कितने बिट में डिफर कर रहे हैं? पहला बिट दोनों का डिफरेंट है? Can we be sure? दूसरा बिट भी डिफरेंट है 01?
Yes, sir.
तीसरा बिट भी डिफरेंट है?
Yes.
चौथा बिट डिफरेंट है दोनों का?
No, sir.
तो कितने बिट में डिफर कर रहे हैं ये लोग? 3 बिट में, राइट? Let me just write this here that DC1, C2 is actually equal to non-zero bits in equal to number of. So let me just write the number of non-zero bits in C1 XOR C2 और C1 plus C2 में वी आर अगेन C1 plus 2 को हम मॉडुलो 2 में कर रहे हैं. जितने नॉन जीरो बिट्स होंगे उसमें आएगा. तो लेट्स कैलकुलेट दिस यूजिंग दिस फॉर्मूला. सो DC1, C2 विल बी इक्वल टू C1 plus C2. क्या मिलेगा हमें? सो नंबर ऑफ बिट्स इन C1 plus C2. सो नंबर ऑफ बिट्स C1 C2 में क्या होगा? 1. C1 plus C2 ऐड करोगे तो क्या मिलेगा? 1 1 1. और ये क्या होगा? 1 plus 1 0. Can you see this? Hello. So how many non-zero bits are here? Number of non-zero. So non-zero bits in 1110. तो कितने 1110 में non-zero bits आ रहे हैं? 3. Is this clear? Okay. So this is what is called as Hamming distance. Okay. And ये जो नंबर ऑफ जीरो बताया मैंने अभी उसको भी हम लोग डिफाइन करने जा रहे हैं. देन इट विल बी मच इजियर फॉर इट. एंड so we call this D. So let me just write this formula and then I will express. DC1, C2 is written as HW C1 XOR C2. ओके. तो HW क्या है? हैमिंग वेट. इसको क्या बोलते हैं? हैमिंग वेट, विच इज आई एम गोइंग टू डिफाइन नेक्स्ट. ओके. मे बी आई शुड हैव डिफाइंड इट विद दैट. So next topic. So this is the very first thing that we discussed is Hamming distance. So Hamming distance, this is something very important and you have to calculate it. You will be getting questions based on this. Okay, that's for sure. So this is the first thing, Hamming distance. Now we are going to discuss Hamming weight. So what is Hamming weight? Hamming weight of a code word, so HW of a code word C is equal to number of non-zero bits in C. ये क्या है? नंबर ऑफ नॉन जीरो बिट्स इन सी. ओके, तो मुझे आप ये बताइए HW ऑफ 1110 क्या होगा?
Three.
And 3, right? When you know the answer, you should speak. And if I'm waiting for you to speak, then you should. What will be Hamming weight of 0, 0, 0, 0?
0.
This is going to be 0. HW of 1100 क्या होगा?
2.
Okay, so I hope that concept of Hamming weight is clear, and so Hamming distance should also be clear, isn't it? Now there is
Yes,
one thing that we are going to define, minimum weight. So Hamming distance, Hamming weight is basically concept of distance and weight. So that is should be very clear. Next topic that I'm going to discuss is called minimum. Minimum distance. And we denote this by D subscript min. Okay, so D means से denote करता है. And what is this? This is defined. So this is defined with respect to a code word. A space of the code word means all code word for a given generator matrix. Okay, for a LBC 7,4 LBC जिसका generator matrix दिया है उसके लिए D minimum defined है. And D minimum is equal to the smallest Hamming distance between any two code word of a code or a block code, for example. Okay, so what does this mean is that you will compute all the distance of the pair. So 0, 0, 0 को 0, 0, 1, sorry ये 7, 0 और ये वाला जो पहला और दूसरा है इनका डिस्टेंस निकालोगे, फिर इसका. So all possible. How many combination will be there? 16 code bits are there and you are 16 C2 ले रहे हैं, right? Combination we are not selecting, we are seeing the combination. So it will be 16 times 15 divided by 2 into 1, isn't it? So basically it will be 15 times 8. तो 15 times 8 कितना हो गया आपका? What 15 times 8 is going to be? क्या है ना, मैं क्या बोल रहा हूँ कि हमारे पास यहाँ पे कितने ये कोड के लिए ये जो कोड हमने पढ़ा अभी इसमें कितने कोड वर्ड है? टोटल 16 कोड वर्ड्स आर देयर, राइट? 0, 0, 0 से लेके 15 तक के लिए. और हमें क्या करना है? हैमिंग डिस्टेंस क्या है? मिनिमम हैमिंग डिस्टेंस. जो इन दोनों में दो कोड वर्ड के बीच में डिस्टेंस जो है वो सारे डिस्टेंस हम लोग लिखेंगे, उसमें जो मिनिमम नॉन जीरो. तो आई थिंक आई शुड हैव रिटन हियर. सो आई मीन मिनिमम नॉन जीरो नहीं, मिनिमम जो कोड वर्ड हो, राइट? तो उसको लिखेंगे. तो अब फॉर एग्जांपल 0 0 0 ऑल 0, पहला दूसरा में कितना हैमिंग डिस्टेंस है बताओ मुझे? 3 होगा फर्स्ट दो में, isn't it? पहले
Yes,
कोड
sir.
वर्ड और दूसरे कोड में 3 डिस्टेंस है, राइट? इसी तरह पहले और तीसरे में कितने हैं? 3। पहले और चौथे में कितने हैं? 4। पहले और पांचवें में कितने हैं? 4। फिर ये देखोगे दूसरा और तीसरे में कितना है? 2। दूसरा और चौथा में कितना है? इस तरह से तुमने जब सारे कॉम्बिनेशन लिए और सारे हैमिंग डिस्टेंस निकाले तो उसमें जो मिनिमम हैमिंग डिस्टेंस होगा दैट इज कॉल्ड एज डी मिनिमम. ओके, नाउ if you see here, तो how many combination हमको लेना पड़ेगा? How many combination are there? So there are 16 and we have to select 2, right, to compare. So 16 into 2 को क्या करेंगे हम लोग? 16 into 15 डिवाइड, 16 C2 कितना हो जाएगा? 16 into 15 divided by 16 divided by 2 into 1, so that is 16 into 15 into 8, and that will be equal to 120, right? So fortunately we don't have to do that. Okay, so this actually in terms is equal to, so D minimum, fortunately it turns out to be equal to minimum Hamming, so sorry, I should have written non-zero Hamming weight. So minimum, let me just write this non-zero in red so that you remember this. Non-zero, let me write this in green, Hamming weight. Weight of all code word of a code. Okay, now we are going to do this. So here we are going to find out what will be Hamming weight of each of these code words. Okay, so next thing that we are going to define is HW. So what is the HW of this first one? Hamming weight of 0 0 0 का क्या होगा Hamming weight? Can you tell me?
0.
0 1 1 0 का क्या होगा?
3.
3. फोर्थ वन का?
Again 3.
सॉरी थर्ड वन का 3 हुआ. फोर्थ वन का क्या होगा?
4.
इसका कितना हुआ?
4.
Right? इसका कितना हुआ?
3.
इसका नेक्स्ट वाले का कितना हुआ? 4.
3.
इसका कितना हुआ? 4. ये 3 ही था ना, 1 1 3 ही है. So this is 3. So that's why it is very important to calculate each code words correctly, okay? Because when this is going to be asked, so this is going to be 3, this is again going to be 4, this is going to be again 3, this is again going to be how much? 4, right? This will be how much? 3. This is how much? 4. And this is how much? 4. And this is 7. So ये सारे वैल्यू में मिनिमम कितना आ रहा है? मिनिमम नॉन जीरो
3.
तो डी मिनिमम कितना हो जाएगा आपका? दैट इज इक्वल टू 3. एंड लेट मी टेल यू व्हाई दिस इज ट्रू. व्हाई हैमिंग डिस्टेंस, मिनिमम हैमिंग डिस्टेंस के लिए हम लोग हैमिंग वेट का ही सहारा ले रहे हैं. द रीजन इज, as I told you, I haven't discussed this topic before, but let me, I mean, there are many small things in these code words. That's why it becomes very difficult. Though they have written it just as a point, it's actually very long to discuss all the properties of linear block code. So one of the property of linear block code, as from the definition only, if you look at the definition that we have, मैंने यहाँ पे वो, चलो sorry, वो गायब हो गया यहाँ से. Let me save this again so that ये कहीं शट डाउन होने पे ना गायब हो. तो हमने जब शुरू में डेफिनेशन बताया था तो मैंने बताया था कि कोई भी ब्लॉक कोड लीनियर ब्लॉक कोड तब होता है जब आप किसी भी दो को ऐड करो, किसी भी दो कोड वर्ड को ऐड करो, 2 या 3 या 4 कितने भी को ऐड करो, तो जो भी रिजल्ट मिलेगा वो भी एक कोड वर्ड होना चाहिए. फॉर एग्जाम्पल पहला और जीरो और इसको ऐड करो, जीरो को तो किसी से ऐड करोगे तो वही रहेगा, राइट? सो दैट इज ऑलरेडी अवेलेबल, राइट? लेट्स टेक वन एग्जांपल, 0001101 को हम ऐड कर रहे हैं 0010110 से, ओके? एंड लेट्स सी व्हाट यू विल बी गेटिंग। इन दोनों का ऐड किया तो आपको क्या मिलेगा? 0011011, राइट? क्या मिलेगा आपको इन दोनों को ऐड किया तो? If you add these two, what is it that you will be getting? Let me do this like this. I'm adding this one and I'm adding this one. So what is इन दोनों को XOR करेंगे तो हमें क्या मिलेगा? ऐड करना मतलब XOR ही करना है यहाँ पे। तो what is it that you will be getting? You will be getting 0 0, isn't it? फर्स्ट दो का XOR किया, फिर 0 1 का 1 आया, फिर 1 0 का 1 आया, फिर 1 1 का 0 आया, 0 1 का 1 आया और फिर इसका भी 1 आया। आया ना? Will we get this or not? Tell me. Will we get this one or not? Hello?
Yes, sir.
Yes. And you see that this is going to be somewhere. So 0 0 1 1, we already know where it will be. 0 0 1 1 कहाँ पे है? 0 0 1 1 यहाँ पे है, right? 0011 का कोड वर्ड क्या है? 0011 011 0011 011। सो ये दो ऐड किया, वो कहाँ पे मिल रहा है हमें? दैट यू आर गेटिंग हियर ओनली। कैन यू से दिस? सो in the similar way, if you add any two, whatever code word you will get by adding them, that will be part of this only. So minimum Hamming distance becomes non-zero Hamming weight in that sense. Okay, and this is only true for a linear block code. It's not true for any other code. Non-linear block code के लिए ये true नहीं है. It is only true for linear block code that minimum Hamming distance turns out to be non-zero Hamming weight. Okay, so is that clear to everyone? Okay.
Yes, sir.
Okay, now let me just fun starts from here again. I haven't it's a very long theory and it involves what you can say that modern algebra that I have already provided a video for, so I can't really go into that because then that will take like forever to complete all these things. Anyway, today we will be able to discuss only linear block code. We will again schedule one more lecture to discuss cyclic code, and then after that we will discuss this convolutional code maybe in another lecture. Okay, so there is just one theorem, and do remember this theorem. So I'm going to discuss two theorems now. So this is theorem, and this theorem says us that n comma k, so n is message bit, k, so n is code word bit and k is message bit, right? N comma k linear block code LBC with a minimum distance that we have written as d min, okay? Part 1 is capable of detecting d min -1 bit error. Part 2. Okay. So we write this as TD. Okay, so TD is equal to how much? D min -1. Again, I can't really go and prove this because that will require linear algebra as well as those field and groups that have already discussed. I'm not going into detail, just remember this. This is something that will be asked in objective examination. So please remember this. Let me just take this 1-2 times so that you understand this, that is important. Okay. And the second part here, so let me just select this and sorry.
So what is TD here?
क्या बोल रहे हैं?
So what is TD?
TD is D minimum minus 1. This is error detection capability. Is capable of detecting D min minus 1 bit error. मैंने बोला ना, तो ये क्या है? इसको बोलते हैं error detecting capability, and this is called TD. TD is equal to D min minus 1. So D min is a very important term that given a generator matrix you will have to determine, and I will tell you shortcuts to find these values. So don't worry about that. We will. Again, there are so many topics here. So anyway, so it's capable of detecting D min minus 1 bit error. Okay. And second theorem, these two theorems are very, very important with respect to any block code, linear block code. Okay. And the second is this code is capable of correcting D min minus 1, this whole thing divided by 2, and then we are taking floor value. So I hope that you do know what floor value is. Okay. Bit error. So this is called error correcting capability, and this is represented as TC. So TC is equal to floor value of sorry, D min minus 1 divided by 2. Okay. So this is going to be your floor value. Error detecting capability, error correcting capability. Okay. Okay. Now let me just warn you that this is the minimum error detecting capability and minimum error correcting capability. Okay. What does that mean? It means that this n comma k block code may be able to detect, let's say, 7-bit error sometimes. Okay. But it may not detect every 7-bit error. But D min minus 1, अगर D min कितना आया? D min वहां पे 3 आया था हमारे कोड में, राइट? यानी D min minus 1 कितना हो जाएगा? 2 हो जाएगा TD. तो उसकी एरर करेक्टिंग कैपेबिलिटी 2 है. इसका मतलब 2 बिट एरर अगर है किसी भी बिट में तो वो कंफर्म डिटेक्ट कर लेगा. इज दैट क्लियर? इज इट क्लियर टू एवरीवन?
Yes, sir.
एंड व्हाट इज द मीनिंग ऑफ टीसी? कि D min minus 1 डिवाइडेड बाई 2 और उसका फ्लोर वैल्यू, यानी 3 minus 1 डिवाइडेड बाई 2 कितना हो गया? 1. 1 का फ्लोर वैल्यू 1 ही होगा, राइट? तो 1 बिट एरर ये करेक्ट हो जाएगा. अगर 1 बिट एरर उसमें होता है वो कोड में, तो वो उसको ऑटोमेटिकली करेक्ट भी कर देगा. ओके. This is the theorem here, and these two theorems are very important because these two are going to be asked to you. Okay, all in quite a few questions. Okay. In fact, when we have theory exam, there was a question in which they were asking you what is error. They will ask you a generator matrix, and with that respect to generator matrix, that they will ask you some code word, and then after that they will ask you what is going to be D minimum, what is going to be TD, and what is going to be TC. Okay. So I hope that these two things are very, very clear to all of you. Okay. Is that all right? इतना समझ में आया आप लोगों को? At least you remember some of these formulas.
Yes, sir.
Okay. So let's just see this example here. So the one that we have already, that's why I said that I'm going to solve this completely. So with respect to this, what is going to be our TC and what is going to be our TD? So TD detecting capability will be how much? D min minus 1, and that will be equal to 3 minus 1, that will be equal to 2, isn't it? What is going to be TC? Floor value of d min minus 1. So this is 2 divided by 2, floor value of this. And this will be equal to how much? 1 only. So ये 1 bit error correcting and 2 bit error detecting आपका ये है. Sometimes you will have 3 bit error detecting, okay, and 1 bit error correcting. Sometimes you will have 4 bit error detecting and 2 bit error correcting, okay. So you will see that we are not randomly choosing this H, okay. We generally choose this H in such a way to provide us certain amount of error correcting and error detecting capability. Okay, and that is something that we will discuss at some other point. But for now, you will have to understand that we are not randomly selecting this generator matrix. Especially generator matrix is nothing but, if you know parity bit matrix, then you will be able to know what is going to be a generator matrix anyway. So we are not randomly selecting it. We are designing it, and that design process, first we have to analyze it. Later on, if you understand this completely, then you will be able to design a 2-bit error correcting or 2-bit error detecting, linear block code. Okay. So that is something that we will discuss at some later point. So I hope that these things are anyway clear to all of you. Okay. Is it clear? Should we move on from this?
Yes, sir.
So next thing that I'm going to discuss, there are still 2 topics here that is left. Okay. So just a minute. So one of those is going to be called parity check matrix. Okay. Okay. So anyway, this is what we were discussing. So what is parity check matrix? That is our question. So parity check matrix is a matrix. We denote it by H. Okay. And this H is a matrix. Then when you multiply your code word C with H, okay. So H transpose, say generally we multiply this. When you are multiplying C with H transpose, this will be equal to 0. Okay, means I'm saying 0 means it is basically it will depending on 0 0 0 मिलेगा. समझ में आ रहा ना? CH transpose is 0. Is this clear? So parity check matrix is H and CH transpose is equal to 0. Okay. And what is C basically? C is message times generator matrix, isn't it? What is C? Code word कैसे निकाल रहे हैं आप लोग in linear block code? We are multiplying M with generator matrix, isn't it? And what does this mean? That M times G times H transpose must be equal to 0. And that basically means that G times H transpose is going to be equal to 0. I hope that this is very, very clear to you. Okay, GH transpose is equal to 0. And H here is our parity check matrix. Okay. Is it clear? समझ में आ रहा है? So what is G? Generally G is I colon P. Okay. And that you are multiplying with H transpose, and that is equal to 0. If you do a bit of analysis here, this H will be equal to, क्या मिलेगा आपको? बता सकते हैं मुझे? What is this H is going to be? P transpose, and this is I of k, okay, and overall this is n by k, isn't it? This generator matrix. So this turns out to be P transpose I of n minus k. Okay, so this is going to be your H matrix. Okay, and this is if G is equal to IK P. Now, if let me just add this. So this is under condition. So if G is equal to IK, I'm not going to prove and all that, though you can easily do this with the help of matrix multiplication. So IKP, then H is equal to P transpose I of n minus k. And if G is defined like this, G can be defined in another way, that P and then semicolon IK, मतलब bit हमारे बाद में आएंगे original bit, then H will be defined in just reverse manner. It will be I of n minus k colon P transpose. Okay. So this is something that you should remember, and we will see how we are going to. So you see that when. Okay, so when we are multiplying this generator matrix, sorry H matrix, parity check matrix से जब भी हम multiply कर रहे हैं कोड वर्ड को, तो वो 0 आ रहा है. यानी हमारा कोड वर्ड करेक्ट है कि नहीं, ये चेक करने का सबसे आसान तरीका क्या है? You will multiply this with H transpose. Whatever code word you receive, you multiply that with H transpose. If you get all 0 code word, all 0 मिल रहा है, इसका मतलब क्या है? That is correct. If you are not getting all 0, it means that is incorrect. Is that clear to you? So P transpose is transpose of parity matrix. Okay. So P is called parity matrix. Let me, मैंने लिखा है कि नहीं पहले नहीं मालूम. So P here is called parity matrix. Okay, I think I have lost that page. Okay. So P is given as parity matrix. I hope that this is very, very clear to you. So should we take a break here? Hello?
Yes, sir.
Okay.
Yes, Sumit sir. Will it be okay if it is 15 minutes?
From my end, it's fine.
Sumit sir?
Yes, it's fine from my end. If it is 15 minutes, there is no problem.
This is 1:20, so we will meet at 1:35. Okay, so you be in the meeting, right? So we just left with only 1 or 2 topics, I think. So I'm stopping the recording.
That is in linear block code only. For cyclic code, it will again take like 2-3 hours. So we will have to schedule that some time else.